Hello, everybody. Can you hear my voice?
Yeah.
Ah, okay, fine. Can you speak up again, please? Okay.
Yes, Professor. I don't know if you.
Okay. Yes, I can hear you.
Yes. Okay.
Okay. Thank you very much. Because I had trouble with my computer. I had to switch the microphone, and I had a previous exercises with students, and I couldn't hear anything, and I tried to fix it during this time. Okay, fine. Well, I received a couple of hints from professor, and he said we should work on multivariable functions. We were on the computation of more variable derivatives, and I think we didn't compute Hessian matrices of 2 or 3 variable functions. Please remember me, because and then we can work on optimization and work with the matrices, and I think not it is not about constrained variables, but unconstrained variables. Something is speaking, maybe, but I can't hear. Someone, sorry, someone wanted to say something. Maybe wasn't that because we were computing some partial derivatives last time. Okay.
Sorry.
Yes, I can hear you.
Can I ask you to solve an exercise about matrices?
Okay.
I will send you the screenshot in the chat, okay?
You can send me a screenshot, or you can...
Yeah. Just
yes.
Excuse me, Professor, can we also do an exercise on time derivatives, please?
Time derivatives of variables of more functions?
Yeah, 2 variable functions.
2 variable functions. Okay, I can see the screenshot. Maybe I can put it directly on the slide. Give me a second. Give me a second. Okay. Give me one more second. I think I have the screenshot saved. Okay, yes, fine. I have the exercise. copied on the slide, and we will solve it. I'm just trying to share the screen. Okay. Okay, now you should see my window with the exercise that your colleague sent to me. Can you see everything?
Yeah.
Yes.
Yeah.
Okay, fine. Okay. So these are exercises about matrices. I thought what is normally a little bit difficult to solve are all the computation with matrices, and this is a good thing to exercise in this case. Okay, let's review how these kind of exercises work by reminding you what the transpose of a matrix is. It is very simple because the transpose of a matrix T. Okay. Maybe this one. The transpose of a matrix. In this kind of exercises, you put the T on the right side above of the matrix A, but you can find many books where the T for transpose is on the left, but I think it is understandable from the exercise. The transpose is a matrix where the rows and the columns, let's take a matrix A where you have A1, 1. It means first row, and it means first column, and you can have as many rows and columns as you want. And for instance, AN1 will be the entry in the position of the nth row and first column. This will be maybe we have let's call M, like many, and M. So Mn, that means the same thing. So we are in the mth row, but the last one will be the nth column. That means A1n is the first of the elements of this column, and we have 1, 2, 3, 4, 5 until m, like many elements in this column that are exactly the number of the rows. So we have m rows and columns. Okay, in this case we have a matrix that has 2 rows. 0, 1 is the first row, and -1, 2 is the second row. If you are considering the columns, for instance, this is the second columns, 1, 2. The places, the entries are A1, 2. The first one means always the row, so it is row 1. and the second entry is A22. Okay. If you want to compute the transpose of a matrix, we will do a couple of examples. You only have to switch rows and columns. Okay, I can write it down. In order to obtain the transpose, switch columns with rows. I hope this says so. That means it is very simple. You have the transpose of the matrix A when you take the first, it is the same. You take the first column 0 minus 1 and you write it down as first row. Okay, same number of row was the number of the column. 0 minus 1 is 0 minus 1. And then you take the second column and you switch to the second row. 1, 2. And this is the transpose. You can notice that if I had chosen instead of first column and second column that become first row and second row, we could have done first row and second row as first column and second column. For instance, the row 0, 1, it is this one, 0, 1, becomes the first column, 0, 1, and the second row, minus 1, 2, becomes the second row, minus 1, 2. As you can see, it is exactly the same because we obtained the same matrix. If you have some matrix, let's say B, that hasn't the same number of rows and columns, you will do the same. Let's say 2, 3, 0, 1, 4, 6. Okay, this is a 2 by 3 matrix because it has 2 rows, 2, 3, 0, and 1, 4, 6, and 3 columns, 2, 1, 3, 4, 0, 6. And when you compute the transpose of this matrix, you will switch rows and columns. That means that it will have exactly the switch indices. So the transpose of the matrix B will be a 3 by 2 matrix. You can choose the columns and write down the columns as rows. The first column is 2, 1, then you have the row 2, 1. Second column is 3, 4, and then you have 3, 4 as row. Third column, 0, 6, and you have 0, 6. You have a new matrix that has 3 rows and 2 columns. I can put a color. Okay, for instance, 0, 6. Okay, there is this is a column, and this will be a row. Okay, so what is the product between matrices? The product between matrices is the product that maybe you know as a scalar product, where you have some vector of a given length and you have to multiply by some other vector of the same length. I will show you maybe in the next slide, and then we can go back to the exercise. But I think Of course, stop me if everything I'm saying now is something that you know very well, but maybe it is useful to to stress on this concepts, because to compute to do operations between matrices, it is very important. So let's say you have to multiply two vectors, and that maybe will be one, let's say, x vector, x1, x2, x3, for instance. And let's take t1, t2, t3, okay. This, and I want to compute this multiplication. This is a row vector. That means it has one row and 3 columns. Okay, I put comma, but maybe you will see often some commas, but maybe it is better too. So, and you have a 3 by 1 column vector. It is what is called a column vector. Column vector. And when and these are particular cases of matrices, because as I told you, you can have matrices with any kind of rows and columns. But in order to multiply these two matrices, you should have the number of columns of the first one that is the same as the number of rows of the second one. I will write it with the red one. The number of the columns of the first and second, because the product multiplication between matrices is not commutative. That means there is a certain order, and you can switch the multiplication between matrices. You can do it only if you have special kinds of matrices. The first matrix should be must be the same as the rows number of the second matrix. Okay, this should be clear. Okay, maybe a little smaller. The number of columns of the first matrix must be the same as the rows number of the second matrix. That means in this case 3 and 3 are equals. It doesn't matter if we have 1 and 1 or any other numbers. We can multiply these two matrices, and the result will be the product of the same number elements of the row and the corresponding column. For instance, you will multiply x1 times t1, and then plus, and then multiply x2 by t2, and then add to the product as x3 times t3. I will write it down, and then we can do directly an example. Sorry, this was t, not x. T2 and x3 t3. Okay, and this is always the same method that you can use for matrices that are have more columns or rows. For instance, let's say you have B1, B2, and B3. Let's give another name. C1, C2, and C3. These are some numbers, some entries. What is the product? I didn't give you the order of the matrix that is the result of this product. The result will have as many rows as the first one and as many columns as the last one, the second one. I will write this. The result is a matrix with as many rows as in the first matrix. The first meaning the first of the multiplication of the product. As many columns as in the second matrix. Okay. That means in the first case, when we computed the product of these two matrices, we will have a 1 by 1 matrix. This is a number because we have a sum of some products. We have a 1 by 1 matrix, an element, only one entry. Only one entry. Okay. In the second case, what do we have? We have a 1 by 3 as the first matrix, a 3 by 2, 3 rows and 2 columns as the second matrix. So the very first checking that you should do is that these numbers are the same, the columns of the first one and the rows of the second one. And then you will compute a matrix as a result that has 1 row and 2 columns. So the result will be a 1 by 2 matrix. Let's do the computations. 1 by 2 means 1 row and 2 columns. So we have some entry, okay, some entry there, and some entry there. Maybe I can take some form, transparent maybe. Okay, so one entry, and then one other entry in duplicate there. Okay, what are we putting inside? This is the place of the new matrix 1 1, A 1 1. Okay, one row, first column, and this is the place first and only row and second column. Okay, these small numbers, these indices, what is the meaning? The meaning is that you multiply first row of the first matrix and the second index, the second place, is the first column. This is called, namely, row column product. Row column product. Column a product. So that means this, let's let's take a different color. Okay, you multiply this first row and the only row. Okay, this is so a blue, and with the green we take this column and let's take another color, yellow, and the second row on the second matrix will be what you are multiplying in this place. So first row multiplied by second column. Let's write the result. It is small, but it will be x. I'm sorry, I should switch to the pen. So you will have x1 times b1 plus x2 times b2 plus x3 times b3. This is a number because this is the result of a sum of some products, but it is one number, one entry. The second one, you have to take x1 and multiply by c1, x2 and multiply by c2, x3 and multiply by c3. So it is only for the room that I don't have, that I'm writing in one column, but it is a sum of more elements. Okay, x3 times c3. That means this will be a matrix with only two entries, two numbers. And if we take the matrix in the previous slide, for instance, the matrix B, and we want to compute the product, let's say between B and A, we rewrite the matrices 2, 3, 0, 1, 4, 6. And then we take the matrix A as is given in the exercise, 0, 1, minus 1, 2. Okay, first of all, we have to check if they can be multiplied. B is a 2 by 3 matrix, and A is a 2 by 2 matrix. Okay, what does it mean? That if we take these two numbers, the number of columns of the first matrix and the number of rows of the second matrix, they are different. So B times A cannot be performed. You cannot multiply these matrices. But if you take another product, A times B, then you will have a matrix that is 2 by 2. And another matrix that is 2 by 3. 2 by 2, and you have to multiply by 2 by 3. In this case, you can perform the multiplication. 2, 3, 0, 1, 4, 6. Okay? Because you have the same number. This is the same. These are equal. You can perform the multiplication. What will be the result? The result will be a matrix that has as many rows as the first one, as A, and as many columns as B. So the result will be a 2 by 3 matrix. Let's compute this matrix. I hope we have enough place. Maybe I can write the matrix B a little smaller. No. Okay. Let's write the matrix B a little smaller, and we perform the computation in this slide. Okay, so we have 2, 3, 0, 1, 4, 6. Okay, so 2 by 3. That means I have 6 entries. 1, 2, 3, 1, 2, 3. 3 numbers to compute. Okay. So what is the first entry of the place 1, 1? Okay. It is the multiplication between the first row on the first matrix times the first column of the second matrix. That means in this place, I use another color. This place will be the product between 0, 1 and 2, 1. Which kind of product? First element times first element, and so on. So it will be 0 times 2 plus 1 times 1. 0 times 2 is 0, 1 times 1 is 1. Okay? So, and let's compute the others. So we will have then in this place, we have again the first row, but the second column. The second column will be the multiplication. This place 1, 2 will be the multiplication between the first row and the second column, 3, 4. So we have to compute 0 times 3 plus 1 times 4. And it is 4. And then let's change color again. So we can complete the first row. We have 0, 1 times 0, 6, the third column, because this will be the place 1, 3, first row and third column. 0 times 0 is 0, 1 times 6 is 6. And so on. We take now the second row and we multiply the second row for every column we have in the second matrix. For instance, this place is the place 2, 1, 2 second row and 1 first column, okay? So, and it is the multiplication between minus 1 times 2 plus 2 times 1. It is minus 2 plus 2, it is 0. The result is 0. In this place, 2 times 2, second row times second column, minus 1 times 3, this is minus 3, plus 2 by 4, it is 8. Minus 3 plus 8 is 5. And the last one, we have second row multiplied by third column. Minus 1, 2 multiplied by 0, 6. So minus 1 times 0, it remains 0, plus plus 2 times 6. Remains 2 times 6, 12. This is the result of this multiplication. And I hope it is clear. And I see that there are some multiplication and we can compute there now. And then we can use the formula for the inverse matrix of a square matrix A, because there is this one to compute. Okay, let's begin with the computation A times B. Maybe I can copy this one and paste in I can copy in only the text, maybe. Okay, so I hope this was clear, as nobody wrote or said anything. And let's perform all the computation on this exercise. So A times B. A times B is 0, 1, minus 1, 2. 1, 2 times 0, 2. Okay. These two matrices can be multiplied because the first one is 2 by 2 and the second one is 2 by 1, two rows and one column. These are the same, they can be multiplied, and this gives you the result of the multiplication. So the matrix, the new matrix will be 2 by 1, okay? 2 by 1. So zero 1 times 0 2 should be the multiplication between the first row of A and the first column and the only column of B. So 0 times 0 is 0 plus 1 times 2. It is 2. This second entry corresponds to second row and first column. So it is the multiplication between the second row of the first matrix and the first row column of the second matrix. So it will be minus 1, 2 times 0, 2, as in the previous multiplication. Minus 1 times 0 is 0, plus 2 by 2 is 4. And this is the result of A times B. Now let's compute transpose of A times X. X, it is a column vector, okay. The transpose of A is 0, 1, minus 1, 2. And the column vector X is X1, X2. Let's do X a little more bold, okay. And the result, what will be? Again, we have 2 by 2 times 2 by 1. It will be a 2 by 1 matrix as a result. Okay, 0 times x1 plus minus 1 times x2. If you want, we can do the steps. Okay, and the second one is 1 times x1 plus 2 times x2, and the result will be minus x2 and x1 plus 2x2. There is a plus in between, and that means that you have only one result. This is the result of a computation. We have 2 entries on this matrix. Okay, then we compute the transpose of B times the transpose of A times X. Okay, there is a rule that maybe you have already seen, of that you are aware that if you have 2 matrices that can be multiplied, that means you must check the different number of columns of the first and rows on the second. But if they can multiply, you have to compute the transpose of a product. The rule says this is exactly as to compute the product of the 2 different transpose of each matrix, but switch. So if you have A times B, what you will have as a result will be the transpose of B times the transpose of A. We won't prove this this rule, but it is very simple, and maybe if you consider, for instance, let's take as A and B, let's only consider the number of rows and columns. Let's say you have a 2 by 3 matrix as A and a 3 by 4 matrix as B. B. Okay, they can be multiplied, and the result will be a 2 by 4 matrix. Okay, what will be the order of the transpose of A? Will be 3 by 2. As we've seen in the previous slide, we switch the numbers of columns and rows. And what will be the transpose of B? 4 by 3. Okay, as you can see, you cannot multiply the transpose of A and the transpose of B because these numbers are not the same. You have to check that you have the same number of columns of the first matrix in the multiplication as the same number of rows in the second matrix. In this case, they can be multiplied. Okay, this is only to this is not a proof, but it explains you why the matrices are of the right order. And so instead of writing transpose of B multiplied by transpose of A, you can take the inverse order and write the transpose of the matrix A times B. We can write it there. Okay, times X. I will cancel what is below. Okay, so we have more room. Okay, and what is the transpose of A times B? This is something that you already computed. That means you only need to take the transpose of the matrix 2, 4 transpose times the vector column x1, x2. Okay, so that means the transpose, you switch columns with rows or rows with columns is the same, but you have only one row. And then you perform the multiplication between these two matrices. This is 1 by 2, this is 2 by 1, they can be multiplied, and the result will be only one number. That means something that has one row and one column. So it is 2 times x1 plus 4 times x2. Normally you don't need to write parentheses because this is only one entry. This is a number, a matrix 1 by 1. The result is 1 by 1 matrix. So you didn't need to compute something special because this is the you can use this rule. This rule is very useful because it holds even for inverse matrices. Okay, because the last exercises that we should compute is the inverse of a matrix A. Sorry. Okay, and we will switch slide. What is the rule for which what is the definition of an inverse matrix? So we can say that A is invertible. You can compute the determinant of a matrix. Okay, I mean you have already done this kind of exercises at the determinant of a matrix, and so let's say. Let's take the matrix A. 0, 1, minus 1, 2. 0, 1, minus 1, and 2. This is, again, the matrix A. The determinant of this matrix is the sum the algebraic sum, the difference between the product of the elements on the first diagonal, so 0 times 2, minus the product of the elements on the off diagonal, 1 times minus 1. 1 times minus 1. Okay, this is 0 plus 1. The determinant is 1. Okay, if the determinant is different from 0, that implies that the matrix A is invertible. Matrix is invertible. Okay, and what is its inverse? The inverse of a matrix A is called a matrix A to the minus 1 if A multiplied by A from each side, and this is one of the many cases in which for which this product is commutative, so we can switch. A matrix, an inverse of the matrix exists if this product is equal to the identity matrix of order n. What is n? If A should be square matrix, okay? So same number of rows and columns, so 2 by 2 or 3 by 3 or 4 by 4 rows and columns. Okay, and if the determinant is different from 0, the matrix is invertible. That means that the product, then you can find the inverse matrix that multiplied by the matrix A gives you the identity matrix of order n. Identity matrix that is, for instance, in 2 by 2 of order 2, it is the matrix that has 1 on the diagonal and everywhere else zeros. This is of order 2. But if you compute, for instance, some inverse and you write down in the identity matrix of order 3, you will have on the diagonal the number 1, and everywhere else you will have zeros. This is the identity matrix of order 3. Why it is called identity matrix? Because if you multiply this matrix by any other matrix that can be multiplied by this one, you will obtain the same matrix. That means if you multiply A by the identity matrix, the result will be A. As the identity number 1, for instance, if you multiply an integer or a real number, if you multiply 5 by 1, the result will be 5, of course. And this is the only case, again, for which the multiplication is commutative. But this holds only if A is square. Okay? Because you could have, for instance, the matrix B, as before, that was 2 by 3. Where was B? This one. Let's take B. Okay. B. Okay. If you take the matrix B, small, and you want to multiply B by the identity matrix, you should choose the right matrix. There are no questions so far. I think because I think it's going good with my connection, but maybe you can hear me.
Yes.
Okay, thank you. Because sometimes maybe I think nobody is there. I I check. So if you want to compute the product between B and the identity matrix, then you should take the right matrix. Which kind of identity matrix you should put on the right side of B? B is 2 by 3. That means you will need an identity matrix of order 3 in order to be multiplied by this one. So you have to multiply by 1, 0, 0, 0, 1, 0, and 0, 0, 1. And you can check that the result will be, again, a 2 by 3 matrix. And the very same of B. We can check the results. The first entry, 1, 1, will be the product of the first row and first column. 2 times 1 is 2, plus 3 by times 0 plus 0 by 0, so it remains 2. And so on, because you have many zeros, and then every time you perform multiplication, that you can multiply. You can obtain the same numbers as in B. This is the result. Okay. For instance, this one, this first row, 1, 4, 6 multiplied by the first column is 1 times 1 plus 4 times 0 plus 6 by 0, it remains 1, and so on. Okay. In the case you wanted to multiply B on the left side by an inverse matrix, then you should have performed the inverse matrix of order 2, like the above on the right, by B. Okay, because this is 2 by 2, and this is 2 by 3. They can be multiplied, and the result will be again a 2 by 3 matrix, that is B. Okay, we did compute the determinant of the matrix A. Okay, the determinant of a matrix is the same as the determinant of the transpose. So a transpose of A will have the same determinant. In particular, this is 1, and the matrix is invertible. And if you have a 2 by 2, maybe you have even a 3 by 3 computation for the inverse. The general rule for the inverse of a matrix is 1 divided by the determinant of the matrix multiplied by the transpose matrix of the adjoint cofactors matrix. I don't know if you wrote this matrix as cofactor, but I think maybe you have multiplied some inverse, and then that means a cofactor is how can I explain? Okay, let's only explain 2 by 2, and then you can tell me if you already did the 3 by 3 and more general examples. So in 2 by 2, so in 2 dimension, you have to divide by the determinant of the matrix times, let's say, I'm sorry, let's say that A is the matrix A, B, C, D, okay, and what you have to compute is you have to switch A and D, so the first diagonal, D and A, okay, and you have to change sign to C and B only, because the cofactor matrix means that in each entry you have a number that is the result of the determinant of what remains in the matrix once you have taken away your entry. But maybe I shouldn't go any further if you don't say that you need to compute the inverse of a 3 by 3 matrix. I think maybe you did, but let me know, because I can give you the rule and we can check if we a computation of the inverse of a 3 by 3 matrix if you want.
2 by 2 is just fine, I think.
Okay, should I give you examples of the inverse of a 3 by 3 matrix with a rule, with a cofactor?
Maybe if you can compute the exercise, I think it's okay.
Okay, so now 3 by 3. You don't need it.
No, thank you.
Okay, fine.
I think.
Let me know. Okay, fine. Okay. So we compute then the result of the exercise that was A minus 1 times B. Okay. So A minus 1 times B is 1 over the determinant of A that we already computed, it is 1. And then this is multiplied by the matrix A, where you can switch the elements of the diagonal. That means 2, 0, okay, because this was the matrix A, okay? And then you rewrite the numbers of the off diagonals, but you should change the sign. That means 1 will be minus 1 and minus 1 will be 1. Okay? Let's check if, I'm sorry, we didn't write B. Okay. Multiply by B, that was 0, 2. Okay, then you have 2 times 0 plus minus 1 times 2. So 2 minus 2, okay. And then 1 times 0 times 0, 2. 1 times 0 plus 0 times 2, it is 0. That means that this computation gives you no, I'm sorry. What? I'm sorry. I wrote the first computation wrong, because 2 times 0 is 0. It remains minus 2 only. only in the second computation will be 0. And so we are done because this is the result of the computation. I won't give you this general rule because maybe you don't need to compute maybe the 3 by 3, only the determinant maybe, because you did compute the Hessian matrix of maybe of 3 variable function, and you computed the determinant of bigger matrices. Okay, I think this is clear. And we wanted to switch to the derivative computation, I think, partial derivatives computation, or some exercise that you had maybe in your slides. You've asked before. I can take some exercise from the book, I think. Because I can check some example. Because you will have more variable function that depends implicitly maybe on the time, I think, and you should able to compute the derivative of the composition of function, I think. So partial derivatives we did compute last time. I think. Nobody writes something. I'll check with examples that I thought maybe could be the right examples. Okay, I take an example from the book. Okay. So let's write a function. So maybe an example that I think it computes the derivative along some curves. I mean, let's take a function of more variables. Let's begin with a function of 2 variables, and then we compute maybe three variables, I think, because I don't know if you wrote the time derivatives with the chain rules. So let's maybe do an easier example. Let's take a function of 2 variables, and you should
We did the chain rule, Professor.
Yes, you did. I only wonder which type of chain rule wrote down, because I was watching the slides of the professor. Maybe something that is the same. For instance, let's say you have you have to derive maybe 2 times. Let's give an example, then you can tell me if it is understandable. Let's say you want to compute some level curves of this function in where the function f of x and y is equals 5, and maybe you want to compute in the derivatives, first and second derivatives, maybe with the chain rule, and you write this equation by writing every variable on one side, and if you derive and you take x and y as a function of the time, let's say y of t and x of t, then you can consider them both as yes. Someone was saying something. You can consider them as both functions. So you derive y square as 2y, but times the derivative of the argument that will be the derivative with respect to the time, that is dy over dt. Y. So, okay. And on the other side, you derive x, and it is the derivative with respect of the time of the variable x. And if you derive once more in order to compute the second derivative, that it could be useful, you can apply the rule for the product of 2 functions. So maybe consider this function and this function as multiplied, and then you compute the derivative of 2y with respect to t, to the time t, and so you have 2y point times the first derivative of y with respect to t that remains, so plus, and then you apply the computation of the product of the derivative of the product, and then you let the first one stay in this in the same form, and the second y you derive with respect to the time twice, because the derivative of y point is written in this case in this form, and then you derive twice, and you have the second derivative in this case. Why it is useful to write it in this in this form, because maybe you could have some function that you can split by computing the first and second derivative. Of course, in economy is something else that maybe in physics or computing force and motion, but you should know that the first derivative with respect to time is the velocity, and the second derivative with respect to time is the acceleration. Maybe we can do another example of unconstrained derivative, because I was watching which kind of a derivative you can compute. Maybe the derivative that we can compute directly by using the formula. Let's say, let's take this other function, maybe with 3 variables, so something like this. So something like so let's take some constant, p times a times x to 1/4 times y. Let's take the same index, the same exponent, so we can compute 3 variables, z to 1/4. Okay, and this is 3 variables. Then I will write f of 3 variables, and x, y, z. Okay, and let's compute maybe the partial derivatives with respect to this may be too complicated. Let's compute only 2. Let's begin with 2. Okay, so you will have to compute the partial derivatives with respect to every variable. Okay, so you will use the rule for df, for instance, over dx. Okay, and then you can compute the partial derivatives in some specific point. So df over dx, you should derive only, so these are constant, only x with respect to x. So we'll have p times a, and you should take the usual rule, so 1/4 minus 1 multiplied by 1/4, as in one variable computation. So that means that you have to multiply by 1/4 and rewrite 1/4 minus 1, that is 1/4 minus 4/4, and that is minus 3/4, x to the minus 3/4 y. Okay, and this is what remains. And as you can see, you could rewrite everything by putting 1/4 and x minus 1, because as we said, it is 1/4 minus 1, okay? And x 1/4 can be put again in the function, and x to the minus 1, so maybe we can write it under the fraction, so as x, and what remains is p a x to 1/4 y to 1/4. That means that it is 1/4x times the previous function, f of x and y, the function of before. And the same computation we can do with respect to the y. And then would be p times a times, this case, x remain the very same, and y will be again 1/4 minus 1, and then we will have 1/4 times y to the minus 3/4, but we can rewrite the same computation and to have sorry, not x but y. There. And then x to 1/4 and y to 1/4, that gives us the derivative 1 over, again, one over 4y times the function f of x and y. And if you want to compute the derivative of the function where we have the function that is the derivative of the previous function, that means the derivative of the function written as y equals a function of x, okay? So this is the meaning of small f. Then you have the rule that you can write as a minus the fraction where you have the derivative with respect to x divided by the derivative with respect to y. With respect to y, as you would switch from the implicit function to the explicit function, and then we can apply the rule, and by consider some curve, some level curve at a given point, and maybe then write the function in a Cartesian plane in x and y. I mean, you will maybe be familiar with something like that. Y, where y is a specific function that you compute explicitly along some level curve. Let's say, I don't know, let's say equals 10, a number like that. And if you want to compute, no, let's give, okay, let's make the computation of the level curve in 4 specific values of x and y, 1/4, let's say numbers that are easy to compute, the 4th square root. Maybe the point could be x0 and y0. So let's say 81 16. Not so much fantasy, but you will take your function, and the result will be f, I write it above, f of these these values that I've just invented. I hope only because the number are easy. So it is the 4th square root of 81 times the 4th root of 16. That means this is 3, this is 2, this is 6 PA that remains constant. This should be given values, but this is 2, this is 3, okay. In this case, if you have these level curves, you cannot apply and compute the slope of the first derivative of the explicit function by substituting in the expression that will be the same as on the right above. So f prime of x is equals minus, and what was the f, capital F? It was 1/4x times the function, and the second one was 1/4y times the function. And as a result, you will have 1/4. You can simplify, because the same function f you have over the fraction and under the fraction. So that means this goes away. And then you will have 1/4x 1/4x divided by 1/4y. That means minus 1/4x multiplied by 4y divided by 1, so as nothing, 4 and 4 you can simplify. Don't forget the minus y over x. And so every time you should compute then the derivative of the explicit function that could be given by some level curve of the function, where the function has a specific value. Okay, in this case maybe where was it, 6 PA. We run out of time. Then you can compute the function exactly in the points that you had as x and y in the level curve. That means in this case you can compute f prime of x0. X0 was 81, some number. So x0, and let's switch slide because we don't have room anymore. So maybe you can compute f prime of x0 as minus, and it was the function was y divided by x minus y divided by x, so y0 and x0. That means f prime in 81 is minus 81 is the same value, and it was y0 was 16. If you wanted to check this value, that gives you the slope of the explicit function. Let's compute 16 divided by 81. It is about minus 1975. Let's say 0.2, and 0.2 is 1/5. Okay, minus 1/5, of course. Minus 1/5, it is 2/10, minus 1/5, and minus 1/5 will be the slope of the function in the point that in a level curve will have x0 equals the value that we gave as an example, 81. This kind of computation are very often. Maybe you can use in many exercises when you have to compute the function, some function in 2 or more variables, where maybe you can add as the function of xy or xy and z some product function.
Professor.
Yes.
Professor.
Yes.
Yeah. Just to understand, why do we use the formula x prime of x, the one below the graph? What is the purpose? I didn't get it.
Ah, okay. I thought you already used this formula. Because
yeah, the professor explained it, but
yes.
that's it. So we have to get a bit of confidence.
Why you use it? Okay.
What for? I mean, what are we looking with the?
Because normally you study the function f, capital F, by given amount of quantity. That means these level curves. So this is the formula for the implicit formula. For the implicit, for the explicit derivative, when you can derive it without compute the explicit formula for the y, for the f small f, okay? Because normally we are not in we are not so good to derive some equation f, capital F equals some quantity. We cannot solve the equation, and we are not able to solve the equation and to put it in a graph where we have only one variable function. That means that if we can, without solving the equation, compute the level curve like this yellow one, and taking the explicit function, then we can compute the formula for the derivative of the explicit function directly without solving the previous equation with the level curves. So this is something that very often that is used very often. That means given the level curves, you could have many of these level curves that you can associate with an implicit function. Let's say we try to compute a function equals 6, 20, 10, some number like I was doing before, okay? And then you should compute the function and find out if the derivative gives you, for example, gives you is convex or concave, and this you can perform by computing the second derivative of the explicit function without do any computation by the capital F function. This is what is called optimization problems. You normally in one variable you can maximize or minimize functions by computing the second derivative of a function. Okay, you have a maximum or minimum if the function is convex or concave. Okay, if it is convex, you have a minimum. If it is concave, you have a maximum. In more variable function, it is always difficult to compute where this maximization, or for instance, if you see as a cost, you want to minimize the cost. If you see as some income, you want to maximize the income. And in more variable function, it is very complicated sometimes, and you have to compute some level curves in order to take from the implicit function the explicit function and do the very easy computation of a second derivative. I don't know if it was the answer to your question. I hope it was helpful for the other.
Yeah, really.
Okay. Okay. Okay, I read this with the point notation. Okay, let's forget the point notation. Okay, as we didn't do that. I think we ran out the time, and I hope it was useful to exercise with this couple of examples, and I will send you as a PDF the notes of these exercises as soon as possible. Maybe I will check the computations before, and then I will send you in the chat like before. Okay, so have a nice day. Yes, someone was speaking.
Yeah, I have a question. Is it possible to upload them on Virtuale? So
to upload?
Can read it?
Sorry?
Upload the notes on Virtuale.
On Virtuale? Because you cannot open this note from the chat?
Well, the last time I couldn't, but I think it's better.
Okay, I don't know if I can. First of all, I will upload in the chat so I don't forget. But I can try to upload the notes even in Virtuale. I will try. Okay. I will try. Okay. You're welcome. Okay, so I hope you have a nice day, and we will see us maybe by the exam or in the next exercises. Have a nice day, a nice week. Good work.
Thank you very much.
You're welcome. Bye to everybody. Bye.